My name is Daniel Dean, and today I'm going to be talking to you about runtime performance anomaly localization for infrastructure as a service clouds. So, as we all know, infrastructure as a service clouds are an effective way to provide inexpensive access to what's normally expensive server resources. And the way that they do that is using virtualization technology. So we have a bunch of virtual machines running in the cloud, and these different virtual machines are leased to end users in a pay-as-you-go manner. So these virtual machines can be running different things and doing different tasks. Some of them might be running MySQL, we might have another one that's running Hadoop, and we could have another virtual machine that's running Apache. And this is all great, and it works really well for end users, but what happens when we have a performance anomaly? Well, when we have some kind of a performance anomaly, something like an SLO violation or a service level objective violation or a service outage, then it's not clear to the end user or to the infrastructure as a service cloud administrator what the actual cause of that anomaly is. So is it something like an internal bug? Is it something that maybe you missed during testing? Or is it something like an external cause? So something like interference from a co-located VM. Or is it your VM's misconfigured? It's not clear to the end user or the infrastructure as a service administrators what the actual cause of that is. And it's important to differentiate between what's between those two causes because the steps taken to actually debug those are drastically different. For internal bugs, you're going to want to collect information and take your system and debug it. For most external problems, though, you can simply migrate and get your resources somewhere else. So this is the problem that we wanted to address. And when we were thinking about this, we looked at what was the state of the art and what's some stuff that's been done in this area to try to address this. The first area we looked at were fault localization schemes. So they try to do things like look at request flows, and they look at the differences between normal request flows and abnormal request flows in a network, and then try to find differences there and localize the fault based on that. Some other stuff is they might look at black box metrics and do something like change point detection in order to try to figure out where the faulty VM is. And these are good, except they can only, the issue is that they can only provide coarse-grained information. They can tell you what VM is affected in the cloud, but they can't tell you if it's an internal or an external, what the cause is of what's affecting that VM. So next we have white box and gray box schemes. Those are kind of on the other end of things. And what these do are, they look at things like using static source code analysis to try to pinpoint where the actual problem's coming from for a particular problem. They can also do things like try to build extensive profiles and then look at differences in function execution times to try to pinpoint things that way. And the issues are that they require, so some of these approaches, they require source code, which simply due to privacy concerns isn't always available in a production level in the cloud. And second, they also require expensive instrumentation. So some of these approaches you might have to recompile your code to put in hooks and to look at what's going on. And that might not be possible if something's already deployed in the cloud. And then third, we have trace-based approaches. So what these do are they try to basically gather a lot of information. They gather user-level and kernel-level information, and then they present that to the user in some kind of a unified view. And these approaches, they'll require extensive profiling, which can take hours and might not be possible if you want to, fix something quickly. So if you want to migrate, if you can just migrate in a few minutes to fix a problem, building a profile and that might be problematic. And then also there's the overhead that these approaches can impart. So by gathering all this, the user level and kernel level information and aggregating everything, they can impart a significant amount of overhead, which isn't going to be viable for a production level tool. So we were looking at what can we do to approach this problem. And in looking at this, we made three key observations. So first, we found that internal faults have a local direct impact. And what I mean by that is only a subset of threads that are actually executing the buggy code are directly affected. We might have other ones that are indirectly affected over time, but there's a subset of threads that are directly affected by the problem. Next, we also observed that external faults have a global direct impact. So if your VM, it's been misconfigured and you don't have enough memory, it doesn't matter what your thread's doing, it's going to be affected as soon as it's scheduled to run. And then lastly, we also observed that system call characteristics provide provide insight for external and internal fault differentiation. And the reason for this is that system call, so user level problems, so these kind of performance anomalies will manifest as either a change in system call execution time or system call frequency. And we can look at this and extract features by looking at the changes in execution time and frequency to help us differentiate internal from external faults. Okay, so now let's take a look at a similar setup, and I'm going to describe our approach to tackling this problem. So we have a similar infrastructure as a service cloud. It's running there's some virtual machines. Everybody's happy. It's cheap. It's working well until a bug happens. So there's a bug in MySQL that causes a service, some kind of a performance anomaly, and the end user is left, or the administrator is left wondering what happened. Now, he doesn't know that it's a bug. And what our approach to do is we continuously trace system calls on the virtual machines. And then when we see that a service or that a performance anomaly actually occurs, we take that system call trace and we pass it to our tool PerfCompass to be analyzed. PerfCompass extracts fault features from this system call trace and then uses those fault features to tell us if there's an internal problem or if there's an external problem. And in this case, PerfCompass would tell us that it's an internal fault. So then the developer, right, he can take, instead of trying to waste time, maybe he migrates and it temporarily fixes the problem, he at least knows that, oh, it's something wrong with my code, and this is something that, that I need to address. So here's a more detailed view of how we actually do our analysis. What we can see here is we have a physical host, and that physical host has an application with a VM. Now, this simplified example, we just have one application in VM, but there could be multiple applications and VMs running here. And that VM has been instrumented with a lightweight kernel tracing module. We used LTTNG for our experiments. And what we do is we continuously trace these system calls. And when this performance anomaly happens, we pass that into PerfCompass to do its analysis. Now, one thing that I wanted to mention is all PerfCompass needs to do its analysis is this system call trace. So as long as that's on NFS, you can run PerfCompass. In this example, it can run on the same physical host. But it doesn't need to be there. You can run PerfCompass in a separate virtual machine. All it really needs access to is this trace to do its analysis. So when this happens and PerfCompass actually starts analyzing things, there's three main components that we do to differentiate between internal and external faults. First, we take the large raw traces and we break them down into smaller, easily processed items we call execution units. Next, we feed those execution units to our fault onset time identification to figure out what threads and processes have been affected and how quickly. And then lastly, we feed that, we look at the results of that and we feed that into our fault localization scheme in order to tell us if it's actually an internal problem or if it's an external problem. And I'm going to talk about each of these components in the coming slides. So while we were designing this, we also had some challenges that we wanted to address. First off, we didn't want to rely on any kind of source code because source code isn't necessarily going to be available in the cloud. We didn't want to rely on source code to do our analysis. And for that, we ended up using a system call-based approach. Next, we wanted to be able to provide details in real time. If you can fix a problem just by migrating, we didn't want to rely on things that are going to take hours to build a model or hours to complete their analysis. So with that, we designed our tool to operate online and to operate quickly. Next, we wanted to make sure that we were low overhead. No matter how good our tool is, nobody's going to use it if the overhead is too much. And with that, we avoided application instrumentation. And then lastly, we wanted to make sure that we can identify both known and unknown problems. And with that, we took an unsupervised approach to things. So we tried to look for things like applying methods like outlier detection, and we didn't want to rely on building like a signature for a particular type of fault. So we tried to make sure that we could identify both known and unknown problems. So here are the three components of PerfCompass, and I'm going to talk a little bit more about them in detail. The first is execution unit extraction. So we have these large raw system call traces, and what we need to do is we break them down into small groups of closely related system calls. From there, then the fault onset time identification, basically it figures out what execution units have been affected by the problem and also how quickly they were affected. So we can determine if it's a direct impact or if it's an indirect impact to this execution unit. And then we actually use that to in our fault localization schemes to tell us if it's internal versus external. So now let's talk about how we actually break these large traces down into execution units. So here's a simplified version of a system call trace. We can see there's 3 columns. We have a timestamp, we have a system call ID, and we have a thread ID. Now the first thing that we did was we break these system calls down based on thread ID, with the rationale being that typically different threads are given different jobs in most applications. So it makes sense to segment things based on based on thread ID. So we can see here that we basically we segment this and we have 3 execution units. We actually found that there were some problems when we were doing this though. We found that there were certain systems, such as like a Apache web server, to avoid the overhead of continuously creating new threads. What they actually do is they use pre-allocated thread pools, and they recycle those threads as needed. So what the thread's doing in the beginning, when it first is created and starts executing, could be totally different from what it's doing 2 hours into the server's operation. So based on that, and also based on just inaccuracy or based on a scheduler, if the scheduler just decides to schedule a thread off, what we did was we further segment these traces, the thread ID traces, based on large time gaps, with the rationale being that if there's a large time gap, that means that the thread has either been scheduled off, it's doing something else, or there's been some significant change in user space. So it's basically been retasked to do something else, or it's executing a different piece of code at the user level. In any case, it's something that the system calls that are going to be generated might not be very closely related. So to mitigate those inaccuracies, we further split this. So then what we can see is that we have this, we've taken this raw trace and we've split it into 4 execution units. So those 4 execution units are then fed into our fault onset time identification. So here's a simple an example to illustrate our fault onset time, how we do our fault onset time identification. What we can see here is this is an execution unit that has some system calls that are executing, and these system calls have some execution time. And what we want to do is we want to basically figure out, is there been any significant increase in either execution time or frequency for this execution unit? Now, the first thing that we noticed was that different system call types can have drastically different execution times based on what they're doing. So for example, IO-based system calls can take a longer time to execute versus like a CPU-based system calls. So with that, what we wanted to make sure that we do is we need to compare system calls of the same type. And then what we do is we basically use sliding windows, and we look at the moving average for these 2 sliding windows. And if we see that there's any kind of a significant increase in system call execution time or system call execution frequency, then we mark this execution unit as affected. So we can see here we have 2 windows. The first window has an average of 5 milliseconds. Everything looks okay. But then in the second window, we see that there's an average of 14 milliseconds. So we can see the last sysread has had a significant increase, and it's basically it's been affected by some kind of a problem. So what we do is we apply outlier detection based on execution time and system call frequency in order to look for this. And the reason that we look at both execution time and frequency is because we found that for some problems can manifest as a change in execution frequency. So for example, if you have some kind of an endless loop, you might not see, your system calls might execute at the same time, but now instead of generating 10 system calls, you're generating 10,000 system calls. So it's necessary to look at both execution time and frequency. So okay, now that we know that this execution unit has been affected, the next thing that we want to know is this a direct impact, or is this some kind of latent indirect impact due to some kind of shared resources or inter-process communication? So in order to figure that out, we calculate the fault onset time. And the way that we do that is we just basically we take the time from the last process system call, which will tell us it's basically the last system call that we processed when we raised the alarm, to the beginning of the execution unit, with the beginning of the execution unit representing when this particular group of system calls was basically scheduled or was generated. So doing that, it allows us to quantify how quickly the execution unit has been affected by this fault. So for this simple example, we can see the fault onset time would be from T7 to T0, or the difference of T7 to T0. So now we know which threads have been affected or which execution units have been affected, along with how quickly they're affected. So the next step is we need to use that information to tell us, is this internal or is this external? The first way that we do that is using a fault impact factor. So the fault impact factor metric, the idea is that if most of the threads are affected and they're directly affected, then that means that this is likely an external fault. It doesn't matter what you're doing. As soon as you were scheduled, you were basically affected by the problem. So if we see that there's more than 90% of the threads are affected, we say that it's an external fault. On the other hand, if we see that there's a smaller number, like a smaller subset are affected, then we say that, well, it's likely, a subset of these threads were directly infected, and it's likely an internal problem. So just a simple, quick example here. We can see that there's several threads executing, and all of the threads have been affected. So in this case, our fault impact factor would be 100%. We would say that it's an external problem. On the other hand, if we see that something like 10% of the threads are affected, that's significantly less than 100%, we would say this is an internal problem. But now, what happens if we're in the middle? What happens if we have 85%? So there's most of the threads are affected, but not all of them. You're kind of in the middle. Well, that brings us to our next our next localization scheme. So with this, what we do is we basically look at the fault onset time dispersion. And what the fault onset time dispersion metric is we made the observation that if all of the threads are affected as soon as they're scheduled to run, all of the execution units, then what that'll mean is if we look at how quickly they're affected and look at the standard deviation among that, well, it's going to be low, right? Because it didn't matter what you were doing. It's going to be you were scheduled and you were affected. On the other hand, if we look at an internal problem, it's going to have a high standard deviation. The reason being that some threads are affected when they're executing the buggy code, and then maybe some guy was waiting on a system log or something, and he was affected down the line. So the standard deviation in that case should be high. And based on that, that's our next localization, or our next differentiation. So if we see that the onset time dispersion is below some threshold, we say that it's likely an external fault because it's been affected very quickly. On the other hand, if it's greater than some threshold, then that means some threads were affected very quickly, other threads and execution units were affected over a longer period of time. So in that case, we say it's an internal fault. And now, one question that I'm sure everybody's asking is, how do we set this fault onset time dispersion threshold? And we found that actually using a static threshold works, but we can also use a calibrated value. So what we found is that different applications interact with the kernel and with different threads in different ways. So what we did was we can set this threshold by injecting a simple external case, something like a CPU cap. Just injecting that and then observing to see how quickly each of the execution units and each of the threads are affected. So based on that, we can set this threshold that we need. Okay, so we've implemented a prototype of PerfCompass in C++. We collected all of our traces using LTTNG, and those traces we were stored on a globally accessible NFS drive. We tested 5 different systems. We tested Apache, MySQL, Squid, Cassandra, and Hadoop. And we tested also 7 real internal bugs, which we found in bug reporting databases. Now, what we basically did was we went to Bugzilla or the appropriate database and just followed the instructions to reproduce the bug. And then we also tested 9 external faults, which represent common multi-tenancy or environment issues. So these type of faults are things like an improperly set memory cap, an improperly set CPU cap, or a co-located VM that's using resources. So here are the results of our external evaluation, or our external faults. We can see highlighted in black are the calculated impact factors for these faults. And we can see all of them are very, very high. Several of them are 100%, if not, like very close to 100%. We have one case that's a little borderline, the MySQL CPU cap, but even that case is still greater than 90%. On the other hand, if we look at our internal faults, we can see that the internal faults are all significantly less than 100%. So we can see most of them are, the 60s, the 50s, 40s. We have one case that's borderline, which is the Hadoop thread shutdown bug. So that's right at 85% where we set our threshold. And when we actually looked at the onset time threshold that we had set with that, we found that it was significantly higher than the onset time threshold. And this, again, this onset time, it was just a simple external case. We just basically set a simple CPU cap and saw how quickly it affected things. We found it was about 39 milliseconds. And then when we compared that to the actual internal bug, we find that that's significantly, the internal bug is significantly higher than our threshold. We wanted to also evaluate the overhead that our system imposes, and we found that our system imposes an average of 1.3% overhead. And this we ran just basically each individual system under a realistic workload. All right, so to conclude, what I talked about today was PerfCompass, runtime fault localization for infrastructure as a service clouds. PerfCompass effectively extracts fault features from large raw system call traces. We're able to successfully perform fault localization in all of the cases we tested. We were lightweight with very little impact to host systems, and we do this without requiring source code or any kind of expensive application instrumentation. So with that, I'll take any questions.
The system calls, did you use any arguments to actually improve accuracy on the measurements?
I see. Yeah, that's actually, so that's a very good question. We didn't use, in our current experiments, we didn't look at system call arguments, but that's one thing that we're looking at potentially, as a way to, that could potentially improve some of our results, especially in the case, if you look at things like IO-based system calls. The execution times, what we actually, the way that we segment things based on, with our execution units, seems to mitigate the case of if you have, a read, if you're doing a read to a 10 gigabyte file, or you're reading, 100 megabytes versus reading, 5 megabytes. And what it seems like is that our segmentation scheme seems to mitigate that, but that would be one thing that we could look at to try to locate these things and further, group things together, maybe to improve the accuracy. So, very good question.
Pradeep Padala from VMware.
Mm-hmm.
Have you considered using logs for doing this instead of the traces?
Logs, you mean like
application
console logs?
Yeah.
So we wanted to avoid that, and one of the reasons that we wanted to stay away from that are there's a lot of work that's been done with console log mining and using console logs to find problems. We wanted to kind of not all applications or not all problems are going to generate console log messages, right? So what we wanted to do is we wanted to try to come up with something that, if there's no console log messages, what do you do? So we tried to come up with something to cover those cases.
Yeah, I think part of the reason is that enabling syscall tracing is going to be tough in any production environment, no matter how low the overhead is, especially because when I haven't looked at the results yet, but when there is high, large number of users for the application, system call trace will go beyond very quickly, right? So even logs can grow very quickly as well. So it might be easier to take the logs approach. There is a lot of work in terms of mining it, but not enough work on detecting anomalies.
I see.
So we can talk offline also.
Yeah. That'd be great. And in terms of the system call tracing, you're absolutely right. It is going to impart overhead, but I guess we can discuss this more offline.
Sure. Yeah. Thank you.
Thank you.
I think I want to add on. I think that here what he does is online processing, so he doesn't store the trace more like days, just like a minute trace. So the size is not information, so that's why it's the online processing.
Sure. Yeah. We can talk.
Great. Any other questions?
I actually had a follow-on. He kind of stole one of the questions I had. I was going to ask a little bit more about using the trace and the overhead that you're seeing. So in the environment you're working on, have you also tested certain types of production workloads, like from an industry perspective? I mean, have you looked at talking to test case customers possibly, or businesses to try this out?
No, so I mean, so in terms of the overhead, the way that we set that up is we basically tried to emulate like a reasonable workload. So we made sure that, you know, the CPU, we were using a reasonable amount of CPU and memory, and we set everything up. So we were going over, not like, we didn't set things up as like a local NFS. We made sure that it was something that we'd have to actually go over the network to. So with regard to that, we tried to make it as realistic as possible. But with the university, it's difficult to really emulate the real world. But we tried our best to make it as close to the real world as possible. Okay. Well, thank you, Daniel. Thank you.